Hey everyone, it's me, Billy Younger. I'm here to solve a Biot-Savart law problem, specifically in an effort to show you how to use the law of Biot-Savart and to glean some principles from it that we can use for other types of problems. So before we start, I wanted to point out exactly how we're going to be using the right-hand rule in this case. In this case, we're actually talking about a current carrying wire that's in a circular loop. So you can sort of imagine this, and here's my right hand. If I grab this wire with my right hand and my thumb is actually pointing in the direction of the current, so that we're imagining the current is going around this way. My fingers are curling around the wire in the direction that the magnetic field would be pointing. So what that means is at each point there's a little magnetic field that goes all the way around the wire in like little concentric circles, and they're going in this counterclockwise direction like that. So if you think about what it's doing over here at the middle, you can see that right here, it's pointing up. The same thing over here. You see right in the middle, it's pointing up. Same thing over here. Right in the middle, it's pointing up. Or, well, pointing this way, which is going to be up in a second. And right here, again, you see it's pointing out this way. So when I have the wire like this, which is exactly the way we're going to have it oriented in this problem, we see that the magnetic field should be pointing up. And I'm specifically only talking about when this wire is flat in a plane like this, and we want to know the magnetic field just at this dead center in the same plane as the wire. So hopefully that helps. Generally, the right hand rule in this case is just basically put your thumb in the direction of the current that the wire is carrying and wrap your hands around it, again using your right hand, and then you look and you see that when my hand is wrapped around it, that means the magnetic field should be going in circles around the wire, in this case, counterclockwise. So that's if the current's coming to you, you should be able to look down at the current and see the magnetic field lines going in counterclockwise circles. And that means that a particular distance away, the magnetic field will have the same strength at that distance away, i.e. at the same radius circle. So right here, the magnetic field will be pointing this way. Right here, it'd be pointing this way. Right here, it'd be pointing this way. And right here, it'd be pointing this way. So hopefully that will help you. But now I want to go ahead and share my iPad screen with you so we can work this particular problem. And let me do that. So this is the current carrying wire that I was talking about. I didn't have the current drawn on it specifically because I had finished erasing the old one from where I worked this in a lecture. But basically what we're going to imagine is that the current is going around in this direction. So that's the current I going around in that direction. And again, using the right hand rule suggests that at the origin, which is the center of the circle, we would have magnetic field lines pointing up from each part of the wire, so that the net effect is that we have a stronger magnetic field at the center than we would for just one wire going by, or four wires going by, or even 100 wires going by if they all had the same current as this one has. So what we're supposed to use here, it says use the Biot-Savart law to calculate the magnetic field at the center of a circular wire carrying a current I. Assume the wire is bent into a circle of radius r. So we're literally imagining this wire as being in the XY plane. The current is all in the XY plane, and the point at which we wish to calculate the magnetic field is also in the same XY plane, and that XY plane being z equals 0. So Biot-Savart law is mu, or actually, let me start by saying dB, the differential segment of magnetic field, dB, caused by a little section of wire carrying a current I in the direction dl, is given by mu 0 I over 4 pi times dl cross rp minus rdl divided by the magnitude of RP minus RDL cubed, where DL is a little differential segment of the wire that happens to point in the same direction as the current I is traveling, and RP is the vector from the coordinate origin, the coordinates that you choose. It's the RP is the vector from the coordinate origin to the point P at which you wish to know the electric or magnetic field, and RDL is the vector from your origin again to the DL vector. So that should give you enough information to know what we got to do. We just got to calculate DL, RP, RDL, RP minus RDL, and the magnitude of RP minus RDL. And once we do that, we can just plug it all in, do the cross product, and then hopefully integrate easily. So to do this, I have to, for starters, choose a section of the wire, and I'm going to call that segment DL, and I'm going to make it a vector by pointing it in that direction of the current, which is obviously counterclockwise as seen from above the positive z-axis. So what I'm going to do is I'm going to take the color green, and I'm going to draw a vector, and this vector is going to be RDL basically. I'm going to draw the vector RDL right there, and that's the vector RDL. You can see it's a radial vector pointing from the origin to a point on the wire. I'm going to say this angle that it makes with the positive x-axis is the angle theta that we recognize from polar coordinates or from uh, other coordinate systems that you're used to, for instance. I'm going to allow now to make the DL, I'm going to allow theta to change from theta to theta plus d theta. And then that will give me another line that'll be the end pointing to the end of the DL vector, only it's not a vector, it's just another line. And that means specifically that I'm going to draw this little DL vector here. I'm going to draw it in purple. So the little DL vector is it's a bit of arc actually. I'm drawing it more or less straight because it's so small, but in reality, it's actually a little segment of the arc of the circle, and this little angle right in here is d theta. Okay, now from what we learned in trigonometry, we know S is equal to R times theta when you measure theta in radians. And oops, let me draw a better circle than that. So if the radius is R and you sweep out an angle theta, then this little arc length right here is S, given by S equals R times theta. So similarly, we should be able to say that DL is going to be R d theta because the radius of the circle is capital R and the extent of the angle is d theta. Now, we also need a direction, and there's a very specific direction associated with this, and I would normally call this direction theta hat, but that's a little more advanced than we normally discuss in a calculus-based physics class, university or physics for scientists and engineers physics course. So what I'm going to do is actually draw this and work out what this coordinate is. So let's start by redrawing this little quadrant that I'm looking at. So I'm going to take my black pen and I'm going to draw the x-axis. And then I'm going to take the black pen and draw the y-axis. And this is going to be the x, this is going to be the y, and I'm not necessarily making it bigger. The main thing I'm trying to do here is just make it flat so we can see it directly. So what I'm trying to do now is I'm going to recreate the same vector things that we had on it. So I had this vector, which was that vector right there was RDL, and this angle right here was theta, and then there was another angle right here, and that's d theta. And all of that was along an arc. And actually, let me go back to purple now. DL was this vector. And I should go ahead and label this other one. This green vector, like I said, is RDL. And that just again is the rate is the vector that points to the location of the DL vector. And this DL we know is actually going to be perpendicular to that radial vector RDL, so I can put a right angle right there. Now, if I redraw the X and Y axes again right there, got a little bit of off axis on that one, but you see I'm trying to draw it straight up and down. That means that this green line that we had, if I continue that on in the same direction as RDL, then this angle is theta. And then we see that that actual direction, that green line, is a radial direction, and this purple vector is 90 degrees ahead of it. So it must be in the direction of increasing the angle theta. So now what I'm going to do is realize that since that DL is 90 degrees ahead of the radial line, then the fact that the radial line is theta degrees ahead of X means that the DL is theta degrees ahead of the y-axis. So this one up here being the y tells us something. And now we can go ahead and further interpret that. If I imagine expanding it a bit, we would look at, let's say, right down here. I'll draw the x-axis again, and I'll draw the dl vector again. So there's my dl, and this angle, of course, is theta. So what I can see is clearly the y-axis is going to be, or the y component of this vector is going to be positive. This would be dl sub y, and the x component of it, dl x, is negative. So from this, we can make the conclusion that dl is actually equal to the magnitude of dl, which is what I'd call this right here. That is dl, but it's also, of course, rd theta, which I'll be putting in a second. But it's easier to write dl. So it's going to be dl times. So now that I have the dl vector drawn and its magnitude dl, which is also rd theta, drawn, I can go ahead and work out what the components are. And the components are going to be, as you can see, negative dl times the sine of theta should be the x component. So I'm going to write negative sine theta negative sine theta I hat. And then the y component is dl times cosine theta. So this one's going to be plus cosine theta. And that's in the j hat direction, so that we can establish it as a vector. Now we can make the substitution that dl is equal to rd theta, which technically has to be big rd theta, even though I wrote little r over here. So that's going to be negative r d theta sine theta I hat plus r d theta cosine theta j hat, and now I can fill in the rest of what the DL vector was above. I'll do it in red just so you can see that we took it from down below, and what I'm going to get is negative sine theta I hat plus cosine theta j hat, and that's my DL vector. Now, additionally, as we look in this second diagram that I did, we can also see that our DL has that as an x component and has this as a y component. So that also allows us to go ahead and say our DL will equal, notice the length is going to be, the magnitude of the vector is just going to be r because it points from this origin to the circular wire, and the radius of the circular wire is r. So all I have to do is take the magnitude of RDL, which is r, and multiply it by cosine theta to get the x component. So r cosine theta I hat, and the y component is just r sine theta j hat. So now you can see from that diagram we got RDL as well as DL. I should point out that this quantity right here is a fairly important one that you'll use in future coordinate systems if you ever take dynamics, statics, or you continue on in physics. It's called the theta hat direction, and the magnitude of this one, the cosine theta plus sine theta j hat, cosine theta I hat plus sine theta j hat, that's actually what we call r hat. So we could also write this as r times r hat, and those two vectors again are basically unit vectors, but as you can see, they're functions as well. So when you have to take the derivatives or integrals of vectors, if they have r hats and theta hats in it, then you have to actually compute the vectors of the or the integrals or derivatives of those vectors. Whereas with you're dealing with I hats, j hats, and k hats, you don't have to. So anyways, now that we have all that, all we need now is RP. And RP is a vector that points from the origin, which is right there where the point P is, to the point P, which is right there where the point P is, and therefore RP is equal to 0. So I can automatically say that RP is equal to the 0 vector, and that gives me that RP minus RDL is just equal to 0 minus r cosine theta I hat minus r sine theta j hat. That means the magnitude of RP minus RDL, which hopefully you can realize is just the magnitude of RDL. So that turns out to be the square root of r squared cosine squared theta plus r squared sine squared theta, which was completely unnecessary because I already told you it should be r, but you can see that that becomes r squared times sine squared plus cosine squared, which is just 1, the one identity that virtually everybody knows. Therefore, we just get R. So that's what the magnitude of RP minus RDL is. And now we've gotten all the vectors we need, and we can go about computing exactly which direction or exactly what the magnitude of the magnetic field is, as well as the direction. As we said, our right-hand rule has already told us we expect that the actual direction of this magnetic field at the origin should be in the positive k hat direction, in the positive z direction, in other words. So now I'm going to go back to working our solution. So b is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral. Now I'm going to write out dl, which is negative r, oh, excuse me, I need to do a big R, negative r, I think I said negative bigative. Don't know where that word came from. It sounded like something from Family Guy. Anyways, negative r d theta times the sine of theta I hat plus r d theta cosine theta j hat. That's going to be crossed with rp minus rdl, and rp minus rdl we already found was negative r cosine theta I hat minus r sine theta j hat, and now all of that has to be over the cube of the magnitude, so that's just a r cubed here. I think you can see that there's a common factor of r in the first vector, and then there's a common factor of r in the second vector, and because of that you get r squared in the numerator, and because of this you get r cubed. Oh, that's r cubed in the denominator, so r squared over r cubed should just be r to the negative 1, which means I'm going to go ahead and pull that out because it's clearly a constant. It's going to be mu 0 I over 4 pi r. Now that means I've gotten rid of the r's in the top, and I've gotten rid of the r's in the bottom as well. Now I just have to integrate. Again, I'm going to pull the d theta out in front too. Put the d theta right here. And even though this stuff is coming after the d theta, us in physics, we tend to use it this way. That does not mean that we don't have to integrate it. We still have to integrate it. So now what I'm going to do is compute. Well, actually, I should probably take another step. I'm going to go ahead and write negative r sine theta. Or excuse me, I already got rid of that and the d theta. So negative sine theta I hat plus cosine theta j hat. Uh, that is the theta hat that I was telling you about in that parenthesis, or in those parentheses. And now in this case, we've got a negative, which I'm going to choose to pull out in front, stick right here. That's going to give me just cosine theta I hat minus sine, or excuse me, that's plus sine theta j hat. This, by the way, is the famous r hat. So let me just take this opportunity again to let you know that this is r hat and this is theta hat. And theta hat cross r hat, if you just look at it, for instance, in this figure right here, this is theta hat and this is r hat. So if you did r hat cross, or excuse me, if you did theta hat cross r hat, then I think you can see that you would get it pointing in the negative x direction, or excuse me, the negative z direction, because with that xy drawn, x to the right and y up, if you use your right hand rule again, your index finger has to point in the direction of the x-axis, your middle finger has to point in the direction of y-axis, and you see z is pointing out of the page. That means the z-axis should be pointing out of the page, just like my right thumb was. So we actually expect that r hat cross theta hat, or excuse me, theta hat cross r hat is going to give us negative k hat. So now we're going to compute that and see if it's actually the case. Technically, I am integrating from theta equals 0 to 2 pi. So I'll just put that in. I meant to put it in blue, but that's good enough. Now I'm going to say negative mu 0 I over 4 pi r times the integral from 0 to 2 pi. Now I'm going to do the FOIL method with the cross product, and we get sine theta times cosine theta times negative. So it's negative sine theta cosine theta, and then it'll be I hat cross I hat, which has to be 0 because it's the cross product A cross B has a magnitude given by the magnitude of A times the magnitude of B times the sine of the angle between them. The magnitude of A and B in this case is both 1, so A is 1, B is 1, and the theta is actually 0, and the sine of 0 is equal to 0, so that's going to go to 0. Now I'm going to take, that was the first, now I'm going to take the outer, so the negative sine theta times the sine theta. That's going to be negative sine squared theta. And this time it's going to be I hat cross j hat. And that's what we get for the outers. And now the inners, that'd be cosine theta times cosine theta. So I'm going to say plus, oops, might help if I keep my pencil on there, plus cosine squared theta. Now this one's j hat cross I hat. So that's j hat cross I hat. And then finally the last, which is cosine times j hat cross j hat. So it'll be plus cosine theta sine theta times j hat cross j hat. But again, we know j hat cross j hat is 0. So I'm going to say this part is 0, just like this part is 0. Now you can use your right hand rule on the XYZ coordinate system we have drawn in the top left here to do I hat cross j hat. I hat cross j hat means you're going to take your index finger and point it in the direction of X, which is out of the board. You're going to take your middle finger and point it in the direction of Y, which is to the left. And now you can see that my thumb is pointing up, and that direction is the k hat direction. So I hat cross j hat is positive k hat. And then j hat cross I hat, you could do the same thing, or you could just realize that a cross b is a negative of b cross a. So either way, you're going to get negative k hat. So what we get is two k-hat terms, both of which are negative. One because the negative sign was already there in the first case, and the other one because the cross product gave us a negative sign. So now I can go ahead and write equals negative mu 0 I over 4 times pi times r times the integral from 0 to 2 pi of, now we're going to have negative sine squared theta plus cosine squared theta times k hat times d theta. And of course, sine squared plus cosine squared is just 1. And we also know that the negative that we see here is going to cancel out with the negative that we see here. And finally, we get an answer that's in the positive k hat direction. Obviously, the integral of d theta, which is all that's left from 0 to 2 pi, is just 2 pi. So we're going to say that the answer is equal to positive mu 0 I over, now the 2 pi from the integral of d theta from 0 to 2 pi is 2 pi. That 2 pi times the 4 pi is just going to leave a 2 in the bottom and an r in the bottom, and it's all going to be in the k hat direction. And that's it. That's the magnetic field at the origin. Oops, I don't know why I drew a 0 there instead of a parenthesis, but anyways, that is the magnetic field at the origin. One thing you might notice also is that, yes, it automatically came up to be perpendicular to the plane that the current carrying wire is in. Yes, we're talking about dead center of the arc, so as long as we're talking about circular arcs and we're calculating the magnetic field at the center of that circular arc in that same plane but perpendicular to it, then we can see that generally the result should be mu 0 I over 4 pi r times whatever the angle will be in radians. In this case, it happened to be 2 pi. So that's going to give us some help in doing other types of Biot-Savart problems, like example 3 that I'm going to show you in the next video. So I hope this was helpful. I hope you've learned quite a bit, and I hope you now know also what theta hat and r hat in are. A lot of times you're going to find, if you take, for instance, dynamics, uh, you're going to eventually find that there's weird formulas like the Coriolis force formula, centrifugal forces, that kind of stuff. Those things turn out to be, a lot of times, just happen to be acceleration terms from Newton's second law, F equals ma, that you can take and pull them from the acceleration side over to the force side, make them look like a force when they're actually just virtual forces. But they're a ramification of this very process of dealing with r hats and theta hats in circular coordinate systems. So if you actually imagine using a spherical or cylindrical coordinate system, and then you imagine the coordinate system rotating about the z-axis, you can get some of these same expressions. You can use the fact that you know what theta hat and what r hat is are in spherical coordinates. You can learn what theta hat, r hat, and phi hat are, and then certain derivatives of those turn out to be the formulas that you use in statics and dynamics, and don't necessarily understand exactly why. So hopefully this helps. I'm gonna go ahead and call it a day. Have a good one. Bye bye.